Let's talk about a few notational things, namely higher derivatives and Leibniz notation. So these are just going to be a couple of things you're seeing in the calculus book as you're reading. I want to address them briefly. First, this idea of higher derivatives. What that means is if you've got a function, say y equals f of x, in this case, let's do an example, let's say sine of x, you know that derivative. For instance, you can write the derivative as y prime or f prime of x, and that's going to be cosine of x. And so what we know from this course so far is that for any value of x that you plug in here, that's going to be the slope of the tangent line to the graph of sine of x at the point x, sine of x. It's also true that this derivative is itself a function, cosine of x. It's a function whose input is x and whose output is the slope of the tangent line to the graph of sine of x. I could take another derivative. Nothing stops me from doing that. So I could take a second derivative. You notate that by y double prime, or you would write f double prime of x. And then what do? That's nothing but taking the derivative of the derivative. So in this case, the derivative of cosine is negative sine of x. So the second derivative of sine of x is negative sine of x. You could take a third derivative, but once again, nothing stops you. And maybe you get tired of writing so many primes, so one thing you'll see is you'll see a little superscript, maybe f, 3 in parentheses of x. And that's notation for the third derivative. And you'll be calculating this by just taking the derivative of the second derivative. The derivative of sine is cosine, so you get negative cosine of x. That's the third derivative of sine. Why would you want to take multiple derivatives? Here's a quick example that comes to us from physics. One of the simplest physical setups, let's say that you're standing on top of the Leaning Tower of Pisa here, and you drop an object. You drop your pizza box off of the top, and it's falling down. And at each point in time, you record the height, h, that it is above the ground. So maybe it starts out at 100 meters, and then after a couple seconds, it ends up at 0 when it hits the ground. And you've got a function, maybe p of t, that just gives you the height as a function of t, as it falls. I use p for position and t for time. And so this has units, and the units here, you could use, well, they're units of distance. You could choose whatever unit you want. You might use meters. When you take that derivative, this has a physical relevance. It's what we call the velocity. So the initial function was your position on the y-axis, your height. Measured in distance or meters, your derivative, that is to say your rate of change of position. In physics, we call that velocity, and this has units of meters per second. Why does it have those units? Because when you take that derivative, you're looking at a limit of difference quotients. So what's the difference quotient? On top, you've got a difference of 2 heights, so that's measured in meters. On the bottom, you've got a difference of 2 times, it's measured in time. So velocity has units of distance over time. What about the second derivative? That second derivative is the rate of change of the velocity. And that's what we call in physics the acceleration. And this is measured now in meters per second squared. So in other words, when you take the derivative of the derivative, So you're taking the derivative of something that's already in meters per second, but when you look at that difference quotient, you're going to have meters per second on top, you're going to have dividing by time on the bottom, so that gives you meters per second squared. So that's where those units for acceleration come from. Now, one more thing about the notation. So this prime notation, I understand, is widely credited to Isaac Newton. At least it grew out of his notational setup. So, and in fact, Newton had a tendency to use a dot over the function to represent the derivative if it was a function of time. And if you go into engineering, or you know someone who's an engineer, then you'll see that too. There was someone else who was developing calculus along the same lines, or at the same time that Newton was, and this was Leibniz, Wilhelm Gottfried Leibniz. And Leibniz had a different notation for the derivative. So instead of writing y prime or f prime of x, Leibniz would write dy over dx. That's called Leibniz notation. And the reason for doing it like that is to remind you that this is a limit of difference quotients. You may have seen this notation of when you're like finding the slope of a line or something like that, to use the delta, the triangle, for the difference. You know, delta for difference. So that's your difference quotient, and then you have to take the limit of the difference quotient to get the derivative. And so what Leibniz did to just make a shorthand for that limit, he just wrote dy over dx. And if you wanted to look at, say, f prime at the point A, the way that he would have notated that is by saying dy over dx. And you draw a vertical line and say x equals a. But they mean the same thing. Now, if you want to write that second derivative, what Leibniz would have done is he would have written d squared y over dy squared. That was his notation for second derivative. So in other words, you're applying this operation of taking the derivative twice, if you like. That's why he's squaring the that little d there.